in the previous section, we have discussed the glomerular filtration rate, mainly the GFR. Before we move on and discuss the tubular functions, because there are three steps in the urine formation: glomerular filtration, then tubular reabsorption, and tubular secretion. And we can say net urine formation is glomerular filtration plus tubular secretion minus the tubular reabsorption. So therefore, before we actually discuss the tubular functions now in this section, I'll just quickly revise what we have done so far in the section of glomerular filtration rate, GFR. And mainly it's because I need to add the Cockcroft and Gault formula for creatinine clearance. So in the previous section, we discussed about the clearance. The formula for clearance is UV upon P. And then we saw P is the plasma concentration of a substance, and U into V is total excretion rate of a substance per unit time. Then we discussed the GFR. Well, at the end of the section, we also saw the rate at which a substance is filtered at the glomerulus. I mean, total filtration rate of a substance or total filtered amount of a substance per unit time. How do you calculate it? Px into GFR. This gives you the total amount of a substance that gets filtered at the glomerulus. Plasma concentration of the substance into the glomerular filtration rate. So that was one more essential point. And then the third thing is, how is GFR measured? It's measured by inulin. I mean, it can be measured. Inulin is the best substance to measure, but commonly used substance is creatinine, and therefore just needed to add a little bit about that. For the creatinine clearance, there is a formula which is commonly in use, which is called as Cockcroft and Gault formula. And this formula says the creatinine clearance is equal to 140 minus age into body weight upon 72 into plasma creatinine. Age in years, body weight in kgs, and that's the formula. And we can understand why certain things have been taken. For example, body weight. By body weight, we will mean muscle mass, because muscle has creatine, and from which the creatinine is generated. Therefore, body weight is important. And age, with advancing age, the number of functioning nephrons will decline, and the glomerular filtration rate also will be affected. So therefore, age is taken into account. That's the Cockcroft and Gault formula. One thing, this formula may not be reliable under certain circumstances. For instance, extreme obesity or advanced pregnancy, because in these scenarios the body weight is not proportionate to the muscle mass. I mean, the body weight is additionally because of the fat mass in case of extreme obesity or in the case of pregnancy, of course. So therefore it would not be reliable under those circumstances, but otherwise it's a fairly reliable indicator of creatinine clearance. So that was how we have dealt with the topic of GFR. Now, having filtered the substances, and of course we have also done the filtration fraction. 20% filtration happens when the substances and plasma passes through the glomerulus. Right. Now it is going to come into the tubules. So therefore, our next thrust will be on the tubular functions. That's the topic in this particular section. Tubular functions. First of all, when the substances are filtered and they start flowing down the tubules, the substances needed by the body will be reabsorbed, and the substances which are to be eliminated will be secreted. So these two functions. Before we start this section, let me tell you an interesting fact. There are two substances which on which all the four processes of kidney take place. All the four processes means these substances are filtered, they can be reabsorbed, they can be secreted, and they can get excreted as well. So all four processes of the nephron are likely to, in fact, they do happen with a few substances: potassium and urea. These are the two substances on which these four processes happen. Third could have been uric acid. It gets filtered, it gets secreted, excreted. But uric acid, for the reabsorption, there are carriers, and it depends. Normally, it would not be reabsorbed, but under certain circumstances, if some drugs are given, like ampicillin and probenecid, those in that case, uric acid can be transported in either direction, reabsorbed or secreted. So, but at least these two you can remember, that all four processes happen. So they will be reabsorbed, they will be secreted. Okay. Now talking about the tubular functions, let's see what all things happen in different segments of the nephron. First of all, let's see how sodium handling occurs along the nephron. Well, sodium of course is reabsorbed from all the segments of the nephron. So how does it happen? First thing, sodium reabsorption can occur in two ways: paracellular transport and transcellular transport. Paracellular is between cells, whereas transcellular means if this is a segment of a particular tubule, and in the tubular fluids there is sodium, transcellular reabsorption means what? It means, look, this is the epithelial cell lining the tubule, and it has got an apical membrane facing the lumen and the basolateral membrane facing the blood vessel. So on the basolateral membrane there is sodium potassium pump, and this sodium potassium pump will remove the sodium from inside the cell and will be taken it into the blood. It causes the sodium concentration within the cell to fall, and then from the apical membrane the sodium will enter from the tubular fluids into the cell. So a two-step process, and therefore this is the transcellular pathway for sodium reabsorption. Now this happens in the loop of Henle, and or rather thick ascending limb of loop of Henle and the distal parts. But in the PCT, sodium reabsorption is mainly paracellular. Remember, paracellular transport of sodium for reabsorption is basically driven by the transepithelial electrical gradient. This drives the sodium movement in a paracellular fashion, and this does not require that much metabolic energy or in the form of ATP, whereas at all other places in the thick ascending limb or in the distal nephron, the sodium reabsorption will involve activity of sodium potassium pump. We have discussed this in the very initial part of the kidney chapter. Therefore, there will be breakdown of ATPs. Right. So PCT, the sodium reabsorption. Let's look at how much gets reabsorbed. 67% of the filtered sodium gets reabsorbed in the PCT. It's mainly by a paracellular mechanism. Apart from that, the transporter that is involved is sodium hydrogen exchanger. This transporter is generally involved in the proximal part of the nephron for sodium reabsorption. And what is the regulatory hormone for the sodium reabsorption? Angiotensin 2, it is known to cause sodium reabsorption. Norepinephrine. So these are some of the important regulatory hormones. Then loop of Henle, 20 to 25% reabsorption of sodium occurs in the loop of Henle. Now, you know, in the descending limb of loop of Henle and in the thin ascending limb, this is the descending limb and then the thin ascending limb, which then leads to the thick ascending limb. Later part is thick. I'm right now talking about the thin descending limb and then the thin ascending limb. Here, now note this, sodium reabsorption occurs mainly by bulk flow, also called as solvent drag. Bulk flow or solvent drag means, look, elsewhere there is a high sodium which pulls water towards it by osmosis. But in this mechanism, water flows in bulk, and water being the solvent, it drags the sodium along with it. So that is the mechanism in the loop of Henle. Now coming to the last part of the ascending limb, that is thick ascending limb. I have taken this as a total 20 to 25% of the sodium reabsorption. But out of that, the thick ascending limb has a separate mechanism for sodium reabsorption. It's a transcellular mechanism, as I mentioned. Sodium potassium pump on the basolateral side. What is the transporter in the apical membrane? The transporter is NKCC transporter. 1 sodium, 1 potassium, 2 chloride co-transporter. It's an electroneutral co-transporter, and the energy for it or drive for it is created by the sodium's concentration gradient. You know that already. Sodium potassium pump has pumped the sodium out, so sodium concentration is less inside the cell, and that creates that concentration gradient for sodium, and therefore that pull is going to cause this movement by this carrier. So that is in the thick ascending limb of loop of Henle. It's a transcellular mechanism of sodium movement or sodium reabsorption across the cell. I hope you have realized by now, when I say transcellular, it means across the cell like this. Right. And what is the transporter involved? As we saw just now, NKCC transporter. Loop diuretics, they will act on this transporter. And regulatory hormone, well, in the next part of the nephron, aldosterone, you know, aldosterone involved in the sodium reabsorption. So it's mainly involved in the distal segments of the nephron. Well then, the DCT, distal convoluted tubule. What is the transporter in the apical membrane? NCC. Well, NKCC transporter is the one on which loop diuretics act, furosemide. NCC is the transporter on which thiazide diuretics act. So that's one point. NCC transporter in the DCT, early DCT. Here is a thick ascending limb of loop of Henle, then the early DCT. As we have already seen, in the apical membrane, there is a transporter, the NCC transporter, and on the basolateral membrane, sodium potassium pump facing the blood vessels. So that's how the transport happens. Again, it can be influenced by the aldosterone. The regulatory hormone is aldosterone. And about 3% or so, 3 to 5% of the sodium reabsorption can occur in the collecting duct. So finally, collecting duct. Now, what is the transporter in the collecting duct? In the apical membrane, there would be ENaC, epithelial sodium channel. So basolateral membrane, as usual, sodium potassium pump, and the apical membrane has ENaC, epithelial sodium channel, also called as amyloride sensitive channel, acted upon by the drug amyloride or potassium sparing diuretics. So that's in the collecting duct. The transporter is ENaC, and its regulatory hormone again is aldosterone involved in the sodium reabsorption. That is how sodium is handled in various segments of the nephron. Now let us see how water is handled. Water handling in different segments of the nephron. Right. First of all, in the PCT, 67% of the filtered water gets reabsorbed in the PCT. So you note this, that 67% of the filtered sodium and 67% of the filtered water get reabsorbed from the PCT. Then loop of Henle, descending limb and thin ascending limb. We have already said about 20% or so get reabsorbed, water reabsorption from the loop of Henle, and by the bulk flow mechanism, water moves out and it drags the sodium. Now the important part coming up. The thick ascending limb of loop of Henle. This part is impermeable to water. This is impermeable to water. So, the NKCC transporter, sodium will be reabsorbed, but water stays back. And therefore, the fluid that will leave the thick ascending limb and reach the early DCT, it will always be hypotonic. The tubular fluid that reaches the early DCT will be always hypotonic. Why? Because sodium has been reabsorbed from the thick ascending limb, but water could not be reabsorbed. This is impermeable to water. So, therefore, the tubular fluid that moves further will be hypotonic. And therefore, now this is an important part. Therefore, this part of the nephron, the thick ascending limb of loop of Henle, is called as diluting segment of the nephron. Diluting segment. It dilutes the tubular fluids. Now next, early DCT some 10% water will be reabsorbed. And finally, collecting duct. Collecting duct. About 10 to 12% water can be reabsorbed in the collecting duct, and that is under the influence of ADH. So collecting duct reabsorbs water under the influence of ADH. When will that happen? When the plasma is hypertonic. When the plasma is hypertonic, there would be signal in the hypothalamus. There will be release of ADH. It will come here and it will cause reabsorption of water. So plasma tonicity will be normalized. Right. That will be about 10 to 12%. So that's the water reabsorption. And because this segment will concentrate the tubular fluids, ADH action will remove water. That means the remaining tubular fluid is concentrated. Therefore, this part, the collecting duct, is also sometimes called as a concentrating segment of the nephron. Concentrating segment of the nephron. It concentrates the tubular fluids. So please remember, thick ascending limb of loop of Henle, diluting segment. Collecting duct, concentrating segment of the nephron. That's one part. Second is, okay, before we move on, let me just tell you a trick question. It always tricked the students. In the full action of ADH, greatest fraction of the filtered water will be reabsorbed from which segment of the nephron? The question is asking, ADH is present and it is acting at its maximum best. Then the greatest water reabsorption will occur from which segment of the nephron? And the options are PCT, loop of Henle, DCT and collecting duct. And very often students read ADH action and they answer the collecting duct, which is incorrect. The question is greatest fraction of the filtered water, even if there is ADH action, always 2/3 of the filtered water is getting reabsorbed from the PCT, irrespective of anything else, irrespective of the plasma tonicity. 67% is anyways getting reabsorbed from the PCT. So whether ADH is there or not there, acting or not acting, greatest fraction of the filtered water is reabsorbed always from the PCT. Okay, so it was a trick question actually. Right. So you need to understand two things: obligatory water reabsorption and facultative water reabsorption. Obligatory versus facultative. Now this 67% fraction which is getting reabsorbed from the PCT, this is called as obligatory water reabsorption. I mean, it is mandatory, it is obligatory to reabsorb this 67% fraction from the PCT. It's irrespective of the body fluid volume or body fluid osmolality, right? So that's why it's called as obligatory water reabsorption. Whereas the water that is getting reabsorbed from the collecting duct, it is called as facultative water reabsorption, in the sense that it depends. I mean, if plasma is hypertonic, then the ADH action will happen. Water will be reabsorbed about 10 to 12% if the ADH action is full, and that's how it will happen. If plasma is hypotonic, then water needs to be removed. So ADH will not be released, its action will not happen, there will be diuresis and water will be lost into the urine. So collecting duct and its water reabsorption depends on the tonicity of the ECF of the plasma, and therefore that is called as facultative water reabsorption from the collecting duct. Therefore, remember, even in the absence of ADH, 88% of the filtered water will get reabsorbed. And in the presence of ADH, when urine is to be concentrated, 99% of the filtered water will get reabsorbed. So ADH is responsible for about 10 to 12% of the total water reabsorption from the nephron. That was about the water handling by the nephron. Let me just add a concept, the concept of free water clearance. Free water clearance. Now, let me just tell you first, what is this concept? What do we mean by free water clearance? Look, kidneys need to either reabsorb water. Whenever plasma is hypertonic, water has to be reabsorbed. Or if the plasma is hypotonic, then the water needs to be eliminated. And that is happening, we saw just now that it's happening by either the action of ADH or lack of ADH action. Water will be either retained or will be lost by diuresis. But there is a problem. The problem is everywhere in the body, water is the solvent. It means there are solutes dissolved in water everywhere in the body, isn't it? Solutes are dissolved. So, they are almost inseparable. Wherever there is water, there are solutes dissolved in it. And therefore, somewhere the water needs to be separated from the solutes so that as and when required, this water, which we call now as solute-free water, okay, solutes and water need to be separated so that whenever required, this solute-free water can either be reabsorbed if the ECF is hypertonic and water is needed, so this solute-free water can be reabsorbed, or it can be eliminated. The solute-free water can be eliminated if the plasma already had a lot of hypotonicity, a lot of water. Then solute-free water can be excreted so that tonicity can be adjusted. So that's the concept of free water clearance. The solute-free water can either be reabsorbed or can be cleared. Eliminated or not eliminated means reabsorbed. So that's a concept. Now, the question is, solutes and water need to be separated. And as I mentioned, everywhere in the body, solutes are dissolved in water. They are almost inseparable. But kidney has this ability, this exceptional ability. I mean, if you are wondering what is so exceptional about this concept of free water clearance, the exceptional thing is that kidney has the ability to separate solute and water, and that's where the whole concept revolves. And mainly it is at two places that kidney can do it. In the thick ascending limb, as we saw just now. In the thick ascending limb of loop of Henle, the solutes are reabsorbed but water is not. Solute and water are separated. First here and then in the collecting duct again. Here the water is reabsorbed but solute will not be reabsorbed if required. I mean, there is excretion of the solutes, the excretory products. So at two places, kidney has the ability to separate solutes and water, and then what it does is solutes are to be excreted finally. You know, the excretory products, particularly of protein metabolism, the urea, the uric acid, and so on, from purine metabolism, the uric acid. So this creatinine. Now these substances, the solutes, they are to be excreted, and if they are to be excreted, some minimum amount of water should be kept for that. So kidney will have this tremendous ability that the solutes which are to be excreted, kidneys will keep some amount of water, minimum amount of water, to keep these solutes in dissolved state. These solutes will be dissolved in a minimum amount of water, and then the remaining water will be separated, and that's the solute free water. And then the kidney will have to decide, in a manner of speaking, kidney will have to decide what to do with this water, which is a solute free water. This is the excretory waste product, and some water will go for that will be excreted. Remaining water, which is separated from the solutes, now the kidney will have to decide that whether to reabsorb this or excrete it, depending on the ECF osmolarity. So that's the concept of free water clearance. So urine volume finally will be the clearance of osmoles and clearance of solute free water. That will constitute the entire urine volume at any given moment, at any given point of time. So clearance of the osmoles and some amount of water kept aside to dissolve these solutes or osmoles of the solutes. And this is the solute free water. And that constitutes our urine volume at any given point of time. Now, if we rearrange the equation, and take osmolar clearance on the other side of the equation, the free water clearance can be negative if the water is getting reabsorbed completely under the influence of ADH. So if the water is getting reabsorbed completely, that solute free water is not getting excreted into the urine, then so let me just put it again. If the plasma is hypertonic, then water will have to be retained, reabsorbed, and urine will be concentrated. So hypertonic plasma requires solute free water to be retained, reabsorbed, and concentrated urine formation. Concentrated urine will be formed because water has been taken out. In that case, the free water clearance will be negative. Water is not getting cleared, it is getting reabsorbed. The solute free water is not getting cleared, it's getting reabsorbed. On the other hand, if it's a hypotonic plasma with excessive water, then the solute free water will be eliminated into the urine. ADH action will be suppressed. There will be diuresis, and that solute free water will be eliminated into the urine. And in that case, urine is dilute. It's not concentrated, it's dilute urine. Water is getting lost, and the free water clearance will be positive in that case. Okay, so concentrated urine will mean free water clearance is negative. Dilute urine means free water clearance is positive, water is getting cleared out into the urine. And the maximum abilities, if you see, when the free water clearance is negative, means water is getting reabsorbed, not excreted. It's up to minus 2 liters per day or so. And if it's getting excreted into the urine, forming a dilute urine, it could go to the extent of 16 to 18 liters per day. That would be the dilute urine formation per day with free water clearance being positive. So this is a positive value and this is a negative value for free water clearance. That's the whole concept of the free water clearance. But the point that I wanted to make was simple. The conceptual point, that is, solutes and water are generally inseparable because solutes are dissolved in water. Kidney has the special ability to separate solutes from water, and then the solutes are to be excreted, so some water is kept aside for that, and then the remaining water which is separated now is a solute free water, and then the kidney will decide what to do with that, whether reabsorb or secrete, depending on the tonicity of the plasma. So that was one more concept which one needs to understand. Okay, now let's summarize the tubular functions next. What all things are getting absorbed in which segments? Let's have a quick summary. Starting with the PCT. Okay, we have already seen that 67% of the filtered sodium and 67% of the filtered water, they are reabsorbed from the PCT. Apart from that, 100% of the filtered glucose, 100% of the filtered amino acids, and 100% of almost 100, more than 90%, almost 100% of the filtered bicarbonate, these are reabsorbed from the PCT. Right. Apart from that, some other substances which are reabsorbed from the PCT, they are 70 to 75% of the filtered chloride, potassium, and calcium. 70 to 75% of these filtered ions, they get reabsorbed from the PCT. Then as we have already seen that the descending limb and the thin ascending limb, there is removal of water and sodium by bulk flow. Then the thick ascending limb of loop of Henle, NKCC transporter, so sodium, potassium, chloride are reabsorbed almost up to 20%. Reabsorption happens in this place by the NKCC transporter, and this part is impermeable to water. Then 5 to 10% of the sodium and water will be reabsorbed from the DCT. Now coming to the collecting duct. Collecting duct. Basically, the collecting duct has two types of cells that you must know. The P cell and the I cell. P cell is principal cell and the I cell is intercalated cell. And to understand it simplistically, the P cell reabsorbs sodium. We are talking about the collecting duct. The P cell reabsorbs sodium and secretes potassium. And then the I cell removes potassium and secretes hydrogen ion. So remember it, In this manner, it will be easy to remember. P cell and I cell. Now, the intercalated cell, it can secrete H plus. It can also secrete bicarbonate. Intercalated cell can also secrete bicarbonate. So this is the buffering cell in the kidney. We already are aware that kidney has an important role in acid-base buffering physiology. Intercalated cell, by removing either H plus or HCO3 minus, plays that crucial role in acid-base buffering. So that's one part. Let me add a few more sentences related to the tubular functions. That is, the glomerular filtrate is isotonic to plasma, and then it starts flowing down the PCT. Okay, from the PCT, 67% of the filtered sodium and 67% of the filtered water are reabsorbed, and therefore by the end of the PCT, the fluids are still isotonic. You get the point? The glomerular filtrate was isotonic to plasma. And then came the PCT. Equal proportion of sodium and water were removed from the PCT. So by the end of the PCT, the fluids will still remain isotonic. Then, coming to the thick ascending limb, where the major action is or major change is happening. Sodium will be removed, but water not. This part is impermeable to water. We have seen this a number of times now. And therefore, water stays back and goes into the early DCT. So, the fluid that is leaving the thick ascending limb, the fluid that leaves the loop of Henle and enters the DCT will be always hypotonic. And then collecting duct, again we have seen this almost twice or thrice now, that collecting duct removes water under the influence of ADH and it concentrates the urine. Finally it's the urine which is being formed in the collecting duct. So there will be a concentrated urine, and therefore this, if we call it tubular fluid, it will be always hypertonic tubular fluid, or finally forming the concentrated urine. Right, that was about the tonicity of the tubular fluids at various segments of the nephron. So these were some important aspects related to the tubular functions. Let me also add one small little concept, and that is transport maximum or tubular maximum. Transport maximum or tubular maximum. It is the maximum rate at which a substance can be transported across the tubule, meaning either reabsorbed or secreted. So transported across the tubular wall, either reabsorbed or secreted. So that is called as transport maximum rate up to which a substance can be transported for the sake of reabsorption or secretion. Well, why is this the maximum rate? Because it will be carrier mediated, and carrier will get saturated at some point of time. So that will be the maximum transport rate for each particular substance. Remember, sodium reabsorption does not have the Tm value. It does not have a transport maximum value. And potassium secretion in the distal nephron does not have a Tm value. Apart from that, all other substances have transport maximum or tubular maximum. They are carrier mediated and they will have these values. So that should be remembered very clearly, that sodium reabsorption along the entire nephron has no transport maximum, and potassium secretion also in the distal nephron does not have a TM value. Let me give you an example. Glucose. What is the transport maximum for glucose? It is 373 milligram per minute in the men and 303 milligram per minute in women. So that is transport maximum. It is the maximum rate at which a substance can be transported per unit time. So otherwise very often the students tend to make a mistake of taking it in milligram percent. Well, you can take the value in milligram percent though. Okay, remember that. If you want to suggest that at what concentration of that substance the carrier will get saturated, okay, then you can take the value in milligram percent, because then it's talking about the concentration of that substance. But we are talking about the rate at which a substance can be maximally transported per unit time. So then we will have to take it as milligram per minute. So either units are acceptable, but this is a rate of transport per unit time. That's more correct way of denoting the transport maximum or tubular maximum. Right, so these were some of the important tubular functions which we had to understand. The next section will be about concentration of urine. So in the next section we will see concentrated urine formation, and then later on we will also discuss the function of the bladder, and finally the acid-base physiology. Alright, so let's discuss another conceptually important topic in the kidney, and that's a mechanism of concentrated urine formation or a hypertonic urine formation. I have already mentioned the steps in the formation of this concentrated urine. There are two steps involved, as you can see. I will be mainly discussing the concept behind it, and then we'll give you some figures and the places where all these things happen. So hypertonicity, that should be generated in the medullary interstitium. The medulla or juxtamedullary nephron is going to produce this hypertonic urine, as we have discussed at the start of the section of kidney, and it achieves this by countercurrent multiplier and countercurrent exchange mechanisms. And then there is action of ADH, which will form a concentrated urine. It will reabsorb water. Let us try to understand the concept behind it. First of all, whenever there is a situation that demands the water to be conserved into the body, that job is given to the kidney, and it's going to reabsorb water. It will retain water from the collecting duct and will form a concentrated urine, because that's the demand of the situation. Water needs to be conserved. Osmoreceptors in the hypothalamus, they are going to sense that the plasma is hypertonic and the water needs to be conserved into the body. So they will send a signal via the ADH. Posterior pituitary will release ADH. It will go to the kidney and will reabsorb water, will cause antidiuresis. But then for that action to happen, for the action of ADH to take place, there should be an osmotic gradient that needs to be created, and a hypertonic environment needs to be created in the nephrons or in the kidney. So that is achieved by various mechanisms in the kidney. which we will see now. Look, kidney is a very smart and sensible organ. For the action of ADH to happen, it needs to create a hypertonic environment. So first thing is, it is possible only in those 15% juxtamedullary nephrons. Remember, at the start of the chapter on kidney, we have seen this, that 85% nephrons are cortical with short loops. Juxtamedullary nephrons have long loops, and this is where it is possible for the kidney to create a hypertonic environment. What I am saying is that if we look at the structure of the kidney, there is a cortex, and then the inner part is the medulla. Medulla also has the outer and inner segments, inner parts. So juxtamedullary nephron with a long loop like this, it is going to play that important role. This is going to form the hypertonic urine by conserving water. How will it achieve this? Look, as I mentioned, the ADH is going to reabsorb water from the collecting duct, and so water is taken back into the blood, and urine is concentrated or hypertonic. But for that to happen, there has to be a hypertonic environment to be created, where in this part, in the medulla, in the medullary interstitium, when this part is hypertonic, it creates an osmotic gradient, on the basis of which then the ADH will act on the collecting duct and will reabsorb water. So that's the basic concept. For the action of ADH to happen, create this hypertonic environment in the interstitium of the medulla. It is possible because of these long loops, as I will mention in some time. But that's the basic concept. That is how concentrated urine can be formed. Now coming to the smart and sensible organs that I mentioned just now, the kidney. You know, hypertonic environment to be generated, to be created in the medullary interstitium, which means what? It means the solutes need to be conserved here. Solutes need to be held back here. Now see, there are two types of solutes. One, which are going to be reabsorbed anyways, and they will go into the blood anyways, like sodium. Sodium is there in the tubular fluids. It is going to be reabsorbed from the tubular fluids, and it will go into the circulation. But before that could happen, kidney can make use of this sodium to generate hypertonic environment. Sodium will be held here in the medullary interstitium to create that hypertonic environment. Imagine that there was just glomerulus and a straight tubule at the end of which urine was being formed. What would have happened? Once the sodium is reabsorbed, then it goes into the blood and it goes into general circulation. It won't help to create that hypertonic environment. But because of the structure, as we will see now, it's possible that sodium can be temporarily held here. Temporarily. It is going to eventually go into the circulation. And the second type of solute in the tubular fluids is the excretory solute. For instance, urea. This is to be excreted. Now imagine urine formation is about 1 to 2 ml per minute or so. if drop by drop urine is being formed and drop by drop the urea is getting excreted, it wouldn't help the economy of the kidney and economy of the body as such. So this excretory solute, which is to be eventually excreted out, even this can be used, this can be utilized. It can be temporarily held here in the interstitium of the medulla and create that hypertonic environment, so that on the basis of that the ADH will act and will remove water. Water will move out of the tubular fluids into the blood and urine will concentrate. So kidney is making use of both these types of solutes or osmoles. The ones which are to be retained into the body, reabsorbed, they will be held here, and the ones which are to be excreted like urea. So instead of excreting urea in a drop-wise fashion, urea will be circulated over and over and over again. Means it will come out of the tubular fluids, it will concentrate in the medullary interstitium, and then urea can also be secreted. If you remember, I mentioned it some time back in previous section that urea is a substance which gets filtered, then it can be reabsorbed, it can be secreted, it can be excreted as well. So this special ability of the urea, since it's a diffusible substance, this special ability is made use of to hold it, to concentrate it, let the ADH act on the basis of that hypertonic environment, and then concentrated urine form. Then the urea can be again secreted back into the tubules and can be excreted out into the urine in a concentrated fashion instead of excreting it in a drop by drop fashion. So it helps the economy of the body and economy of the kidney as such in a great way by this smart and sensible action of the kidney. With that, let's now try to understand what all things are happening here. So let's start first. As I mentioned, first thing that will be created is hypertonicity in the medullary interstitium. We have already seen this, that here is a medulla, the inner part, and outside the nephron is the interstitium. So creating hypertonic environment there. That's the first step, so that the ADH can act. Now this is achieved by the counter current multiplier mechanism, and it is maintained by counter current exchange mechanism. So at the outset, let's try to understand that the hypertonicity in the medullary interstitium is created by the so-called counter current multiplier mechanism, and then it will be just maintained by the counter current exchange mechanism. Let's look at them one by one. Now first thing, as I mentioned, if it was a straight tubule like this, glomerulus would filter the sodium, filter the urea, and then sodium will be reabsorbed, it will go into the blood and general circulation, and urea will be excreted out in a drop by drop fashion. Instead, what's actually there, the structure of the nephron, is in the form of a counter current flow. So first thing that you should make note of is the counter current flow of tubular fluids. That is, there is a loop of Henle, the descending limb and the ascending limb, and then again the collecting duct. So the fluids are going down in the descending limb, then they go up in the ascending limb, and again go down in the collecting duct. This is the counter current flow. So it helps. In what way? In sodium getting retained here in the interstitium, and urea also can be recycled in this manner if it is going up, and then it can be reabsorbed from the collecting duct, inner medullary collecting duct. It will come into the interstitium, and then once the urine is concentrated, urea has to be excreted, then it will be secreted back and it will be eliminated out of the body. So first things first, the counter current flow itself helps rather than what could have possibly been this kind of a nephron. Now coming to the next part of the word, counter current multiplier mechanism, counter current multiplication. First point, where does it all start? Counter current multiplication, it starts in the thick ascending limb of loop of Henle. This is where it all starts. Thick ascending limb of loop of Henle. So that's the first point, that the counter current multiplication starts over here. What do I mean by starts over here? Look, there is a glomerular filtrate. Glomerular filtrate is formed and it is isotonic. It is isotonic to plasma. Let's say 300 milliosmoles per liter, the tonicity. Now it starts flowing down the tubules. And then when it reaches the thick ascending limb of loop of Henle, it all starts here. We have already seen this in the previous section, that kidney has this tremendous ability to separate solutes and water. So you should concentrate on that, because water needs to be either excreted or it has to be conserved. I mean, concentrated urine formation is happening. So otherwise solutes are dissolved in water. They are almost like inseparable, but kidney can separate them, and it can separate them at these two places: thick ascending limb of loop of Henle and then the collecting duct. These are the two places where kidney separates solutes and water, and that is all what is going to matter. Look how we have this tubular fluid with the tonicity of around about 300 milliosmoles per liter. Now what happens is, the thick ascending limb of loop of Henle is impermeable to water. Impermeable to water. And it is permeable to solutes. So there is a transporter called as NKCC, 1 sodium, 1 potassium, 2 chloride co-transporter. It's an electroneutral transporter, as we have already seen, that 2 cations, 2 anions, like that. So it brings out these solutes, especially sodium and chloride. In fact, they say that the most important initiating factor for counter current multiplication is the movement of chloride, because chloride being the anion, it creates an electrical gradient then for the movement of sodium. So single most important determinant or driving force for counter current multiplication is the movement of chloride. So these solutes, particularly sodium and chloride, they will now come out into the interstitium, whereas water has not come out. So this is where it all starts. Now what happens is, because water has stayed back in the tubular fluid and sodium has come out, so tubular fluid will become hypotonic, let's say 150 milliosmoles per liter. That will be the tonicity of the tubular fluid, and the sodium and chloride have come out, so it will be hypertonic, 300 milliosmoles per liter. No water, only the sodium and chloride. So that is how the medullary interstitium begins to become hypertonic. This part, the interstitium, it begins to be hypertonic. Now what I want to say here is that there is something called as horizontal osmotic gradient. You can see here from tubule to the interstitium in a horizontal manner. If you look at it, the horizontal osmotic gradient is 1:2. Clear, very obvious, 150 to 300. And vertical, when I say vertical osmotic gradient, that means for the entire interstitium from above downwards, it is going to be 1:4, and I'll come to that in just a moment. But just remember, for now, 1:2, the horizontal osmotic gradient, like this, across the tubular wall into the interstitium, and vertical gradient is 1:4, which we will see just now. Right, but so far so good. We have understood this much, that the sodium has come out. Now it will be held over here. We will see that when we discuss the counter current exchangers. But now this 300, what happens next is the descending limb will cause some movement of water, so that the osmotic equilibrium is reached between the interstitium, the interstitial fluid, and the tubular fluid in the descending limb. So for the time being, I am taking the same figures for the sake of explanation and to avoid confusion. Otherwise, I know if the water moves from here to here, this tonicity will decrease slightly. But for the sake of explanation, let's take the same figures, that the descending limb, it goes into osmotic equilibrium. So now even the tubular fluid has become slightly, it is going to become hypertonic as more and more fluid comes in. See how? New glomerular filtrate will form, and this new glomerular filtrate will cause this fluid to be pushed forward. This will be pushed. It has started to become hypertonic. The tubular fluid just started. So this fluid will now start moving along the loop of Henle, and then again when it reaches the thick ascending limb, what will happen now? Yes, again sodium and chloride will be removed and will come into the interstitium. So this time, let's say the osmolarities will become 200 for the tubular fluid and 400 in the medullary interstitium. So in this manner, there is going to be multiplication of the salts, multiplication of the solutes. More and more solutes will come, and then they will be taken out into the interstitium from the thick ascending limb, and then tubular fluids will go into osmotic equilibrium with that, and then more and more solutes, the filtrate will come in. So this is going to be the addition and multiplication. So counter current multiplication has begun. And as I said, interstitium and the descending limb over here, they will reach the osmotic equilibrium. So now descending limb has some amount of concentrated tubular fluid or hypertonic tubular fluid, and as the new filtrate comes in, this tubular fluid, which has begun to become hypertonic, now it is pushed further along the loop of Henle, and then the solutes, the new solutes which have got filtered, they are getting removed from the thick ascending limb. So in this manner, the osmolarity of the medullary interstitium will rise and rise and rise. So Now, look, juxtamedullary nephron has a long loop. That is advantageous. Because it has got a long loop, so there is a lot of space in the interstitium. There is a lot of vertical space in the interstitium, and therefore the more and more solutes could come in the interstitium, so that the tonicity of the interstitium could increase and increase and increase. And you can see here at the very bend of the loop of Henle, we can say at the tip of the loop of Henle or this bend of the loop of Henle, the tonicity reaches 1200 milliosmoles per liter. So medullary interstitium can maximally become hypertonic up to 1200 milliosmoles per liter. First of all, I mentioned some time back 1:4, the vertical osmotic gradient. See, 300 to 1200, 1:4. But that much could reach, that 1200 milliosmoles per liter could reach because of such a big space that was available, and that was because of the long loop of Henle. The cortical loops, the cortical nephrons have shorter loops, so it could not go on increasing, the distance would be less, but this long length helps there. Right. So now coming to the point, and that is the maximum hypertonicity that could be reached is up to 1200 milliosmoles per liter in the medullary interstitium. And therefore then, when the ADH acts on the collecting duct and takes the tubular fluids into osmotic equilibrium, even the tubular fluids in the collecting duct can have the osmolarity of up to 1200 milliosmoles per liter. Now this is the final urine formation, and therefore maximum hypertonicity that can be reached, maximum hypertonic urine or concentrated urine can be up to 1200 to 1400 milliosmoles per liter. In 1 liter urine, 1200 to 1400 milliosmoles per liter can be excreted. Well, if you want to remember it, you can remember it as 4 times the plasma osmolarity. Plasma osmolarity is taken to be 300 milliosmoles per liter, and 4 times that is the maximum concentrated urine or maximally hypertonic urine. Why it is 1200? We have seen that already. So that is the summary of counter current multiplication mechanism. Let me just add something about the urea. What role is played by the urea? Because we have seen that the sodium and chloride, which are needed by the body, they were taken out from the thick ascending limb. Eventually they will be going into the circulation, but they are retained here temporarily. Now let us see the urea, which is an excretory product. I mean, it's going to be excreted, but before that, how it can contribute in this mechanism? Look, almost 50% urea is taken out. It's not reabsorbed, but it's just taken out from the PCT. Then as the urea comes here, this entire loop of Henle is impermeable to urea. Urea cannot move out. It then goes to DCT, and for the first time urea can be reabsorbed or taken out into the interstitium is from the inner medullary collecting duct. Here is the collecting duct. So it's from here that for the first time urea will be removed. It will be taken out into the interstitium. So here is the interstitium, and even this part, this is the interstitium, this is the interstitium. And as I said, inner medullary collecting duct, if this is the medulla, then it will have an outer medulla, and then the inner medulla. So inner medullary collecting duct. From here the urea, and why urea? Because urea is very highly diffusible. It can diffuse rapidly. Well, let's also say urea is diffusible means by facilitated diffusion. There are urea transporters which are called as UTs, UT1 and UT2. These are the urea transporters, and how the urea movement occurs, it is influenced by the ADH. Yes, urea movement occurs by ADH, because when ADH will cause reabsorption of water, there will be, from the collecting duct, what will happen is there will be a huge concentration gradient for urea from the tubule toward the interstitium. There will be a concentration gradient for the urea, and by that the UTs, the transporters, can then cause movement of urea into the interstitium. Urea can be transported back, secreted back into the tubules as well. But just remember, urea transporters are influenced by the action of ADH. Okay, now urea plays one or two important roles. One is, look, as I mentioned, that when medullary interstitium becomes hypertonic, then the descending limb is going to reach osmotic equilibrium with the medullary interstitium. How? By movement of water, isn't it? How the two fluids reach osmotic equilibrium? By movement of water between the compartments. So there will be movement of water from the descending limb into the interstitium, because this part was hypertonic, the interstitium was hypertonic. So this hypertonicity is threatened. Now that is where urea comes in. Urea will neutralize that the threat to the hypertonicity which is caused by the movement of water. So urea contributes in this manner. Let me add, if we are saying that maximum hypertonicity which is reached is 1200 milliosmoles per liter, then almost half of it is contributed by urea. So let's say 40 to 50% of contribution comes from urea, and remaining 50 or 50 to 60% comes from the sodium. That is the contribution of the two solutes, sodium or required solutes and excretable solutes. Right, that's one part played by the urea. And this is the counter current multiplication mechanism for sodium chloride, and then the role of urea that is contributing to create this hypertonicity, to add into that hypertonicity. The second part is counter current exchangers. Now look, this counter current flow is helping to maintain the solutes in this region, right? If the solute could not be reabsorbed from one place, it could be reabsorbed from the next place, but it can be brought out and it can be secured in this place. So counter current flow itself is helping in that way. But then when the solute comes out into the interstitium, there will be blood vessels, and that solute, whether it's sodium or whether it's urea, but mainly sodium, it goes into the blood, and then it will go into the general circulation because it's required in the body. So it will go away. Now that is prevented by the blood vessels in the medullary interstitium, which is called as, those vessels are called as vasa recta. Recta means straight. So straight blood vessels. Here is a loop of Henle in case of the the juxtamedullary nephron, the long loops, and positioned alongside this long loop, the blood vessels are the vasa recta. So even vasa recta have this kind of counter current blood flow. Even they have the descending limb and the ascending limb. Only thing is, in front of the thick ascending limb, there is the descending limb of vasa recta. So blood is going down here, and in front of the descending limb of the tubule, there is the ascending limb of the vasa recta. The blood is going up. In a way, we can call this also as counter current, isn't it? It's going in the opposite direction. The tubular fluid going in the ascending limb, thick ascending limb, the blood is going down. So in a way, that also is a counter current. Well, but that's besides the point. The point is that because of this arrangement, the solute which has come out, sodium and chloride, can be held here. So the point that I'm trying to make is, vasa recta do not actively contribute in the creating that hypertonicity in the medullary interstitium, but they prevent it from dissipating. You get the point? I'll just repeat once again. Vasa recta will not actively contribute in creating that hypertonicity, 1200 milliosmoles per liter. They won't contribute directly, but they prevent it from its dissipation. That 1200 milliosmoles hypertonicity should not be dissipated. The solute should not be washed away from the interstitium. That role is played by the vasa recta. Let's see how. First thing, very important part. First thing is, of course, the blood flow. Okay, it's in a U-shaped pattern like this. That's one advantage. Second is, vasa recta have a sluggish blood flow, a very important component that is going to help. Why this is a sluggish blood flow? Because of the fact that they have long lengths like this. Because of the long length of these loops, even the long length of the blood vessels, vasa recta, and because of this long length, straight length, what is going to happen is the hydrostatic factor will take place as you go down, and there would be an increased viscosity. So because of these two reasons, as the blood goes down into the descending limb of vasa recta, it will become sluggish and sluggish and sluggish. So, and then this sluggish blood flow will see to it that the solutes which have come out, they have come out into the interstitium, they will enter the blood vessel, the vasa recta, and they can be delivered back into the interstitium. They do not go out of the interstitium into the general circulation. So sluggish blood flow helps there. Remember this. I am making an important statement, so listen to this. That if the blood flow in the interstitium increases, the rate of blood flow, it becomes fast, then the solutes which have come out in the interstitium, they will not be maintaining here. They will be washed away from this region into the circulation, and that means the concentrating ability of the kidney will be lost, impaired. Why? Because it was all dependent on creating the hypertonicity in the interstitium. Only then the action of ADH could act. So that's an important part that one must understand. Sluggish blood flow. I told you why it is sluggish, and I also mentioned what will happen if the rate of blood flow will increases. Right. So Now let us see the exchange mechanism. They are called as exchangers. Vasa recta are called as countercurrent exchangers. So let's see how. The sodium which has come out from the thick ascending limb, as the blood goes down in the descending limb, it will take that sodium, it will take the solutes and give out water. Water will be given out. Okay. So please listen to this. The descending limb of the vasa recta, which is in front of the thick ascending limb, it will take that sodium, it will take the solutes which have come out, and it will give out water. Of course, it's a blood, so there will be water in it, and water is given out. Why water is given out? Because as I told you, as you go down, there is going to be hydrostatic factor. And hydrostatic factor, remember we have done Starling's forces, capillary hydrostatic pressure. It's a force that pushes the fluid, pushes the water out of the blood vessel, isn't it? So water will go out, and therefore as the blood is going down in the descending limb, the blood itself is going to become hypertonic. You get the point? Because the sodium is coming in and water is going out. So as one goes down and down, at the tip of the vasa recta over here, the blood will be maximally hypertonic, 1200 milliosmoles per liter, because that's the maximum tonicity that can be generated. And then as the blood starts going up in the ascending limb, the opposite will happen now. That is, water is taken back and solutes are given out. Sodium is given back into the interstitium. So, the blood that goes out of the interstitium will be hypotonic because it has taken back water into it and it has given out sodium. So it is going to be hypotonic. Maximally hypertonic blood at the tip of the vasa recta, and then it becomes hypotonic as it leaves the interstitium. So, but that's why it's called as exchanger, that it causes this exchange while going down and then again going back up. Vasa recta are the exchangers. So remember all this. This is quite a quick summary of the countercurrent mechanism in general. But what you should understand is the sluggish blood flow helps. It maintains the solutes in this region. Otherwise, they would have been washed away from this region, and that won't help. Increased blood flow in this region decreases the ability of the kidney to concentrate the urine. Right. So vasa recta playing this role. I repeat once again, they do not actively contribute in that hypertonicity up to 1200. They only maintain it. They prevent it from dissipating. That's it. But that's also important in the overall scheme. So that is the countercurrent multiplier mechanism and countercurrent exchanger mechanism. Finally, then on the basis of this hypertonicity which has been generated here, ADH action will happen and water will be removed from the collecting duct and urine will become concentrated. So that's how concentrated urine formation can occur whenever the situation is demanding. Right. That was one section, important one conceptually. Let's move slightly ahead from this. And the next part is, therefore, maximally concentrated urine. We have already mentioned it, but just as a quick recap, 1200 milliosmoles per liter, and max dilute urine or hypotonic urine or dilute urine can be up to 50 milliosmoles per liter. ADH action will be stopped and there will be diuresis and a dilute urine will be excreted. We have also discussed the concept of free water clearance in the previous section. Well, now moving on, or rather just the next point is that an average healthy young adult, a young average adult generally has to excrete at least 600 milliosmoles of solutes per day. You must remember this. The minimum that is excreted every day into the urine is about 600 milliosmoles over 24 hours. Now then, what is the maximum concentrating ability of the kidney? 1200 milliosmoles per liter in 1 liter. So assuming that the urine was maximally concentrated, how much urine volume will be required to excrete 600 milliosmoles over 24 hours with maximally concentrated urine? Half liter, isn't it? Because the maximum concentrated urine is 1200 milliosmoles per liter. So to excrete 600 milliosmoles, half liter will be needed. And therefore, 0.5 liters per day is called as obligatory urine output. Obligatory urine output, meaning this much is a must. I mean, urine output cannot be less than this, because 600 milliosmoles have to be excreted. It could be more than that, okay, more than 600, but at least 600 are to be excreted every day. And if the urine was most concentrated, even then half liter is required to eliminate 600 milliosmoles. So therefore this is called as obligatory urine output, half a liter per day. And remember, this is like the bare minimum required. If the urine volume is less than that over 24 hours, less than 500 ml, means let's say 400 ml or less per day, will be then called as oliguria. Right? So you now know why oliguria is when urine output is 400 ml or less per day. And less than 100 ml per day would be actually called as anuria. One more point, that most hypotonic urine is 50 milliosmoles per liter. That's most dilute urine. And we are saying at least 600 milliosmoles of solutes are to be eliminated every day. Now, assuming that the urine is most dilute, 50 milliosmoles in every liter, then to eliminate 600 milliosmoles, how much will have to be the urine output? How much will have to be the urine output? Come on, calculate. 50 milliosmoles in 1 liter. So to excrete 600 milliosmoles per day, 12 liters per day will have to be the urine output with the most dilute urine. And this I am saying is the minimum excretion of solutes, 600 milliosmoles. I am saying at least 600 are have to be excreted every day. It could be more than that. So remember, with most hypotonic urine, the amount that is eliminated every day is 12 liters per day, and maximum urine output with zero action of ADH and most dilute urine can increase up to 18 liters per day. That's the maximum possible output of urine. So these are some of the things related to the concentrated and dilute urine and the solute excretion. Right. So we have covered a lot of ground related to the nephron function. We started with GFR and We discussed the clearance concept, the free water clearance. We have seen the tubular functions, concentrated and dilute urine, and finally these aspects. So we have discussed those parts which are very routinely asked in the entrance exams, and therefore we go on to the next sections. One is bladder function is remaining, and then acid base physiology, which we will discuss in the end. So let's discuss the urinary bladder and the micturition reflex, or the process of micturition. Right. Let's see quickly the functional anatomy of the bladder. What all things are there? First of all, the detrusor muscle. Well, the very basic fact, I don't think it's even required to be discussed. Once the urine has been formed, then the ureters will bring it down into the bladder via the ureteric peristalsis. Yes, there is ureteric peristalsis, and for the ureteric peristalsis, the pacemakers are also there, which are located at the junction of or the pelvic calyceal junction, at the upper part of the ureters, and then the urine comes into the bladder starts filling. Well, wall of the bladder is having the muscle which is the detrusor muscle, and then urethra, it will have the internal urethral sphincter and the external urethral sphincter. Now, most of these things are under the parasympathetic control and therefore automatic or involuntary, except external urethral sphincter. I mean, what I wanted to say is that external urethral sphincter is the one which is under voluntary control, because although what is the function of the bladder? To hold the urine so that it can be passed in one instance. I mean, urine formation is taking place at 1 to 2 ml per minute, but then passing of urine cannot be at that rate. So urine will be filled and then periodically emptied. That's the function of the bladder, but there should be proper time and place. Until that time, the urine flow cannot start, urination cannot start. That's the function of external urethral sphincter, that unless it relaxes, micturition cannot start. So it will hold back the process of micturition until a proper time and place is there, suitable time and place. Right. So if you see the innervation of the bladder, let's just draw it here once again. Innervation has, as I mentioned, parasympathetic innervation from the spinal cord, the S2, S3, S4, the sacral segments, sacral parasympathetics. So the reflex arc from the bladder wall, it involves S2, S3, S4 segments, which are the parasympathetic nerves. Sympathetics, are they involved? Well, sympathetics are not involved in the micturition reflex as such, not involved in the process of micturition as such. They are involved in conveying the pain sensation from the bladder. So if the bladder is filled beyond 500 ml or so, 600 ml, then there will be pain from the bladder wall. So that sensation is carried by the sympathetic nerve. The other thing is about the external urethral sphincter. External sphincter. Now that's under the control of pudendal nerve. You know, pudendal nerve is a somatic nerve. So it will have the conscious control over the external urethral sphincter. Now, by the way, you must have read this in anatomy that there is a nucleus of this pudendal nerve that regulates this voluntary function. Onuf's nucleus. Anyway, that comes in the part of anatomy as well. You will read it there. But then that's one part. And then we have two more centers. Look, this is a reflex arc, but this reflex arc needs to be regulated properly. So we have pontine centers. Let's draw it here. The brainstem center or the pontine micturition center, which is called as Barrington's center. And the micturition reflexes themselves are called as Barrington's reflexes. So remember, anything that's related to the micturition, you can say Barrington's reflexes or center. Brainstem, the pontine micturition center can have facilitatory nerve cells and the inhibitory nerve cells, so that the reflex arc can be facilitated or inhibited. Apart from that, there is another center in the cortex. Frontal lobe, paracentral lobule. Frontal lobe, paracentral lobule. We have micturition center, which is only inhibitory center. Inhibitory center. So, cortex can voluntarily inhibit the onset of micturition till a proper time and place is available. And therefore the cortex, human beings, because of their evolution of the cortex, they have these inhibitory centers which keep a check till a suitable time and place for every activity. In fact, apart from micturition, any activity, cortical influences are predominantly inhibitory in nature, which we will see in the CNS, of course. So cortex and its inhibitory control over the external urethral sphincter, that is how it can voluntarily hold back the onset of micturition. So these are the centers, and this is the functional anatomy of the bladder. Now let me just say how it all happens. Onset of micturition is that as the urine starts getting filled in the bladder, there would be stretch of the proprioceptors in the wall of the bladder. Okay, proprioceptors in the wall of the bladder are stretched, and then the signals are sent to the spinal cord. The signals are also sent to the higher centers, and if there is a proper convenient time and place for micturition, then the reflex arc will be facilitated by the pontine micturition center. The reflex arc will be facilitated, and the first event that will happen is contraction of the detrusor muscle. So if some question comes, the first event in the process of micturition, the answer is contraction of the detrusor muscle, because so far it was just a signaling regarding the filling of the bladder. But then, if the onset has to begin, the facilitatory impulses will come down, the signals are sent to the bladder, and detrusor contract. So that's the first event in the act of micturition. Now remember also one thing, that micturition reflex is a self-regenerative process. It's a positive feedback, which means it will go on becoming stronger and stronger and stronger. It will start as a weak signal, but it will go on becoming stronger and stronger and stronger. So in that sense, it's a self-regenerative process. And how it all happens is that contraction of the detrusor followed by immediately, these things are happening very rapidly, so it will be followed by relaxation of the external urethral sphincter. Internal has been relaxed already at the same time by these parasympathetics. Relaxation of the external urethral sphincter, which was under voluntary inhibition Now once that relaxes, few drops of urine reach the posterior urethra. That now, more and more of the same is going to happen. That's why I said it's a positive feedback. So first few drops reaching the posterior urethra, urethral wall is stretched, and the receptors in the wall of the urethra, they are stimulated. They will send the signals back to the cord, and reflex will be strengthened and strengthened and strengthened. So remember, the micturition process becomes stronger and stronger and stronger, and that is how bladder will be emptied. That's the process of micturition with the onset of micturition reflex. Okay, let me just add two more things here. One is cystometrogram, the pressure volume relationship of the urinary bladder. Well, if we look at the graph, and here is a pressure cm of H2O, here is a volume of urine in the bladder in ml, and the landmark volumes will be 100 ml and 400 ml. So cystometrogram is the pressure volume relationship of the urinary bladder. It has three phases. Look, up to 100 ml filling in the bladder, there is phase 1A. Then from 100 to 400 ml, there is phase 1B. And beyond 400 ml, there is phase 2. So that's a cystometrogram. That's how it appears. And the most striking feature of this is the 1B, phase 1B. You can see here that bladder is getting filled from 100 to 400 ml, but there is hardly any rise in the pressure in the wall of the bladder. The graph is not going up. Why is that? The answer is Laplace's law. Yes, you have done this in physics. So Laplace's law is applicable to any hollow viscous or hollow sphere. It says pressure in the wall of the viscous or the sphere is directly proportional to the tension but inversely proportional to the radius. P is equal to 2T upon R. So the bladder itself, hollow viscous, this law is applicable. What happens from 100 to 400 ml is, as the tension in the bladder wall increases because urine is getting filled, radius of the bladder also goes on increasing, and therefore both numerator denominator increasing, therefore pressure remains the same. It does not increase much. And beyond 400 ml in the bladder, what happens is, now the radius cannot increase any further. When more than 400 ml is filled in the bladder, now the radius cannot increase, just the tension goes on increase in the bladder wall, and therefore pressure goes on increasing. So beyond, after 400, there would be a urgency of micturition. As you can see, the pressure in the bladder wall is increasing quickly. So that was cystometrogram. And if I were to just put this in the numbers, let's write it down. 50 ml in the bladder is said to be the residual volume. After every act of micturition, some 50 ml stays back, and that's called as residual volume. Entire bladder is not completely emptied. 50 ml stays after every act of micturition, and it's a residual volume. Then 100 to 150 ml will be the first reflex from the bladder wall. It will start, as we saw, from 100 ml onward. Although the graph is not rising much, but there may be intermittent reflexes from the bladder wall. Just they would not cause any desire for micturition. They would just indicate some amount of filling of the bladder. But then 250 ml filled in the bladder would be first desire for micturition. And then we have already mentioned beyond 400 ml in the bladder, 400 to 450 would be the urgency for micturition. Well, I know that many authors might have mentioned that first desire for micturition will be at 150 ml. Somewhere it is mentioned that the urge for micturition or desire for micturition, some authors have mentioned it's at 150 ml. I beg to differ on this, simply because already 50 ml is there in the bladder after the last act of micturition, and just some 50 or 100 ml filled and there is desire for micturition, that means urinary frequency will be too much then. Okay, so it will be just an indication that the bladder is filling, that's it. But urge or desire will start only at 250 ml, and then still the person will have a time to find the proper time and place for micturition, because after 450 ml the real urgency will start, urgency for micturition. And then more than 600 ml in the bladder would be a painful urgency for micturition that will be carried by the sympathetic nerves. Up to 800 ml is said to be the physiologic capacity of the bladder. Up to that point, urine can somehow be held back in the bladder. But if it's 800 ml is reached, then urine can't be held back by any means. So that's called as a functional capacity of the bladder. And then 900 ml is the anatomic capacity of the bladder. Purely from the anatomic standpoint, how much is the total capacity in terms of volume? So that would be 900 ml. These are some of the numbers related to the bladder function. And finally, although the next part that I am going to discuss briefly is discussed in the medicine in detail, so I may just give a quick summary of that. The effect of lesions at various levels. Effect of lesions and what kind of bladder it will produce. So, read it in medicine once again, because very often there is an overlap of topics, so there should not be any contradiction. I will stick myself to the physiological part and the related lesion. So, lesion. First, if the afferents from the bladder are cut, section of the afferents from the bladder wall, it results in an atonic bladder. Atonic bladder, bladder wall loses its tone completely. Next is if the lesion in the sacral segments of the spinal cord, sacral segments, it will result in an automatic bladder. The automatic bladder is the one in which the bladder goes on getting filled and goes on getting evacuated. It's just goes on automatically without any control from the brain stem center or the cortical center. So it becomes an automatic bladder. The next is lesion higher up in the spinal cord. So let's say a condition of spinal shock. Spinal shock condition. You know what happens in the spinal shock condition? Suppose there is a transection of the spinal cord and it has resulted in the spinal shock. All muscles will initially lose the tone. So tone loss for all the muscles. But when the stage of recovery happens from the shock condition, what happens is the sphincters regain their tone. The sphincters regain the tone, whereas bladder wall remains flaccid. I'm talking about the spinal shock condition from which the recovery is happening when there is a section higher up in the spinal cord. So, sphincters will gain the tone, regain their tone, but bladder wall is still flaccid, and this will result in overflow incontinence. So, that's another thing, overflow incontinence. That is, the bladder will go on getting filled up to its capacity, and then when the intravesical pressure, here the vesicae means bladder, so when the intravesical pressure is good enough to overcome the sphincteric resistance, some drops of urine will dribble out. So that's called as overflow incontinence. Do you understand this? Very often the students ask me this question, what is the difference between an automatic bladder and an overflow incontinence? In automatic bladder, some urine is filled and then it is evacuated. Some urine is filled and then it's evacuated. So it's very regular and periodic. It happens regularly. Whereas in this case, bladder will become almost full. Full means up to its quite a maximum capacity, and therefore the intravesical pressure rises, and when that pressure can overcome the sphincteric resistance, few drops will dribble out, and then again retention of urine. So retention with overflow, that's the picture in this particular case. And finally, further up, the section higher up in the spinal cord, which sections these nerves, the corticospinal nerves, or the nerves that are coming from the cortex, or we can say the lesion between cortex and pontine center. Now that results in the bladder, which is called as, it has 2-3 names. It's called as neurogenic bladder, or it's also called as urge incontinence, in the sense that once there is urge for micturition, then the urination cannot be held voluntarily. There will be urination involuntarily. I mean, voluntarily it cannot be controlled. And why is that? It's because cortex was the inhibitory center. It was voluntarily holding back that onset of micturition, which is not possible if the lesion is like this. So it's also called as spastic uninhibited bladder. These are the names for the same lesion, spastic or uninhibited bladder. So inhibition is not possible because of the lesion, and therefore onset cannot be voluntarily held back. Once there is urge, then urination will start. And midstream holding also is not possible. Normally, cortex can inhibit the act of micturition even midway through, but that also midstream holding of urine also will not be possible if the lesion is like this. So these are some of the types of bladder, and we have discussed the bladder function, cystometrogram, micturition reflex in a positive feedback fashion, the numbers related to the bladder. So we have covered a lot of ground in the excretory system. What is left is the acid-base balance, which we will discuss in the next section. Now the pH of the body fluids, we saw just now that the pH of the ECF is 7.4, or intracellular pH is 7.2. So it is quite far away, right? But still, bicarbonate buffer is the most plentiful buffer in the ECF. So please remember, the major chunk of ECF buffering occurs by the bicarbonate buffer system. It's the most plentiful buffer in the ECF. Next, phosphate buffer. Before we talk about the phosphate buffer, let me just add one more ECF buffer in this. Hemoglobin also is a buffer. You know, the oxyhemoglobin is a good donor of H plus, and deoxyhemoglobin is a good acceptor of H plus. So hemoglobin is an excellent buffer, and hemoglobin is an ECF buffer. Hemoglobin is an extracellular buffer. Quite obviously, because although it is inside the RBCs intracellularly, but the fluid that is available for buffering is the extracellular fluid, right? And therefore hemoglobin is also an important buffer. Its buffering ability is mainly because of the histidine residues in the globin, right? Coming to the phosphate buffer, pKa of the phosphate buffer is 6.8. So now this is closer to the 7.2, which is the intracellular buffer, and therefore phosphate buffer is most important at two places. Intracellular buffering, some amount of intracellular buffering occurs by phosphate. You know, intracellularly there are phosphates, and renal tubular fluids. Phosphates, they do get concentrated in the renal tubular fluids. Almost 8-time concentration as compared to plasma is found in the renal tubular fluids. So at these two places, phosphate is an important buffer. And the third chemical buffer is intracellular proteins. Intracellular proteins. These are the most important intracellular buffers. More than 70% of the intracellular buffering is achieved by the intracellular proteins, and most of these proteins have their pKa's in the range of 7.1, 7.1 or so, and that's quite close to 7.2, and therefore major chunk of intracellular buffering is by the proteins. Major chunk of the extracellular buffering will be bicarbonate, right? So these are the chemical buffers. And now we'll see the respiratory buffer system and the kidney. Let's look at the respiratory system. As I have already mentioned, the acid-base disorders are of two types basically: respiratory acidosis alkalosis or metabolic acidosis alkalosis. Well, respiratory acidosis means what? If there is a respiratory depression, so CO2 cannot be eliminated out of the body, CO2 accumulates, and CO2 means H plus. We have done that already. So it will result in respiratory acidosis. Now, since respiratory system is unable to eliminate this H plus, it is not functioning properly, the correction or the compensation will be done by the kidneys. Kidney will excrete the acids and pH will come back to normal. On the other hand, if it's a metabolic acidosis or alkalosis, why would there be metabolic acidosis? The reason is the metabolic acids were generated, but kidney was unable to eliminate those acids. So problem is with the kidney, and then the metabolic acidosis or alkalosis will then be compensated by the respiratory system. I mean, for example, if there is metabolic acidosis, it will stimulate the respiratory system and the CO2, and therefore the H plus will be washed out of the body, right? So respiratory system is the physiological buffer, as we have seen already. It takes 3 to 12 minutes for its full activation. Now, when the respiratory rate is doubled, pH will increase by 0.45, and when the respiratory rate is halved, then pH will decrease by 0.23. This goes to show that respiratory buffer is a more stronger buffer in the acidic pH as compared to alkaline pH. Look, acidosis or alkalosis, both can be compensated by the respiratory system. But if we compare, we find that respiratory system is a stronger buffer for acidosis and in acidic pH compared to the alkaline pH. And the proof is this that I told you just now. Look, respiratory rate, when the respiratory rate is doubled, means what? Respiration was stimulated. Why was respiration stimulated? Because acids accumulated in the blood, and acids means there was a condition of acidosis, and those acids, they will stimulate the peripheral chemoreceptors, and that will stimulate the ventilation. So ventilation was doubled. Instead of respiratory rate, let me write, when the ventilation is doubled, pH will increase. You know why? Because then the CO2 will be washed out of the body. CO2 washed out means H plus washed out. So if the acids are washed out, the pH will rise. pH will move towards alkalinity, or it will rise. And on the other hand, if the ventilation is halved, what is the meaning of that? Ventilation halved means ventilation depressed. So this will happen in alkalosis, isn't it? In alkalosis, the ventilation gets depressed. In acidosis, it gets stimulated. So alkalosis, then ventilation was depressed, and as a result, the acids have accumulated and the pH has fallen by 0.23. The change of pH was 0.23. So you can see that it was a stronger reacting buffer when there was acidic pH. There was an acidic pH which doubled the ventilation, and that resulted in this change in the pH. And when there was alkaline pH or alkalosis, it depressed the ventilation, and this was the change in pH. So lesser change has happened, and therefore it is said that respiratory buffer is stronger in the acidic pH, right? And we also saw how it can correct the conditions of metabolic acidosis or alkalosis by wash off of CO2 and H plus, or retaining the CO2 and H plus. Right. Now coming to the third buffer system, and that is kidney. Kidney plays the role of buffer in three ways. There are three functions in the kidney that are meant to be the buffering functions. One is reabsorption of the filtered bicarbonate. Second is, whenever required, there will be generation of the new bicarbonates. And three, the kidneys have ammonia buffer system and the phosphate buffer system, which we saw some time back. Right, so these are the three ways in which the kidneys act like a buffer system. Let's look at them one by one. First, the reabsorption of the filtered bicarbonate. Some part of it we have already discussed when we discussed the bicarbonate reabsorption or filtration. Let's look at it once again. You know, how much is the total filtered amount of bicarbonate per day? We know this now. Px into GFR. That is how we can calculate the total filtered amount of a substance per unit time. Plasma concentration of the substance into GFR. So, bicarbonate has a plasma concentration of 24 milliequivalent per liter. And since it is in liter, let's take it in the liters. The GFR 180 liters per day, and therefore the total filtered bicarbonate amount is 4320 milliequivalents per day. This is the total filtered amount of bicarbonate every day. Now this has to be reabsorbed because the cells are producing acids, and therefore we need the bicarbonates as well to be retained in the body. So most of it, more than 90% or more than 95%, most of the bicarbonate will be reabsorbed. The bicarbonate, most of it is reabsorbed from the PCT. That's the first point. Now bicarbonate is in ionic form, and you know ionic forms are less diffusible. So bicarbonate reabsorption from the PCT will not be that easy. How then the bicarbonate is reabsorbed from the PCT? Is by the secretion of H+. Secretion of the H+ in the PCT. So remember, H+ is secreted in the PCT. To reabsorb 4320 milliequivalents of bicarbonate, equal amount of H+ will have to be secreted. Look, what will happen is H+ will be secreted and it will combine with this HCO3 minus to form H2CO3 that splits into CO2 and H2O, and then you know the diffusion of those is possible. Once it enters the cell, and then it's going to be reabsorbed. So again it will form H2CO3 that will split into H+ and HCO3 minus. So that's how bicarbonate can be reabsorbed, only when it combines with the H+ which got secreted. Okay, I'm talking about the filtered bicarbonate. It is to be reabsorbed. It's needed to neutralize those acids produced by the cells. So now if this much is filtered and all of it is to be reabsorbed, equal amount, that is 4320 milliequivalents of H+ are secreted by the PCT. Okay, so H+, how much is secreted by the PCT? 4320 milliequivalents to reabsorb that much bicarbonate. And this secretion is said to be along the concentration gradient, and it's meant for reabsorption of the filtered bicarbonate. So the point that I'm making is H+ secretion by the PCT is not for the urinary acidification. Okay, it is meant for reabsorption of the filtered bicarbonate. But hold on, the collecting duct will also secrete the H+. If you remember, we have done this in the tubular functions, that there is a P cell and there is a I cell. The P cell reabsorbs sodium and secretes potassium, and then I cell reabsorbs potassium and secretes H+. Okay, so H+ is also secreted by the collecting duct. Now this H+ secretion is for the urinary acidification. Acids to be removed into the urine and urinary acidification. Now this H+ secretion is against the concentration gradient. We saw in the PCT it was the H+ secretion was along the concentration gradient. The collecting duct secretion is against the concentration gradient, and about 80 milliequivalents are additionally secreted by the collecting duct. So total H+ secretion, per day will be 4320 plus 80 milliequivalents, and that is 4400 milliequivalents per day. This is called as total acid output per day by the kidney. Out of that, 4320 is gone for the reabsorption of the filtered bicarbonate, and 80 milliequivalents is called as net acid output by the kidney. So please remember, It can be asked as a factual thing, how much is the net acid output per day? It is 80 milliequivalents. Okay, that will be net. Basically, kidneys have to titrate the H plus and HCO3 minus levels in the body. pH of the ECF will be known, and H plus and HCO3 minus. So these will be titrated against each other, and then kidneys will have to see, okay, H plus acids are in excess, they have to be eliminated. If the acids are less and bicarbonates have increased, for example, there is respiratory alkalosis, then this I cell can also eliminate bicarbonates into the urine. So urinary alkalinization is also possible. Right. That was the first point. That is how kidneys are the buffer system by causing reabsorption of the filtered bicarbonate, and you can remember these mechanisms as well, which we saw just now. Okay, let me just add one more point here, because we are talking of the acids elimination into the urine and the buffering done by the kidney. The H plus secretion in the collecting duct is against the concentration gradient, and the concentration of H plus in the tubular fluids is 1000 times. What I'm trying to say is the ratio of the H plus in the plasma is to tubular fluids would be 1:1000, or that much concentration will be of H plus ions into the collecting duct. That is maximum possible H plus secretion. That H plus will get 1000 times concentrated in the collecting duct tubular fluids. And when that happens, when maximum secretion has happened, the pH of the tubular fluids will become 4.5, and this is called as the limiting pH of the tubular fluids. 4.5 is called as the limiting pH of the tubular fluids. I mean, maximum acidic urine can be up to 4.5, not less than that. Okay, so that's the limiting pH, and that's the role of H plus secretion to reabsorb the bicarbonates or to eliminate the H plus independently in the collecting duct. Right. Second mechanism by which kidneys they function as a buffer system is generation of the new bicarbonate. You know, sometimes just the filtered bicarbonate may not be adequate to be reabsorbed and to titrate against the H plus. So what happens is the buffering cell in the kidney, as we have said already, intercalated cell is the buffering cell. It can secrete H plus, it can secrete HCO3 minus. It can generate the new bicarbonates. Do you understand the situation? These reabsorbed bicarbonates, they were already present, they were already generated, they were already present in the body fluids. They got filtered and they got reabsorbed. But new bicarbonates also can be generated by the kidney. You know, one molecule of glutamine will produce 2 ammonia molecules, and in the process 2 new bicarbonates are generated and are added to the ECF. Right? So this cell metabolizes the glutamine to generate 2 new bicarbonates, and at the same time 2 ammonia molecules are also generated. So that's how new bicarbonate generation. And the third way of buffering in the kidney is by ammonia and by phosphate buffers. So let's see a few things about these buffers. Ammonia buffer. First of all, ammonia, as we saw just now, ammonia is generated from the metabolism of glutamine, and then ammonia will come into the tubular fluids and bicarbonates will be added into the ECF, into the plasma. Now this ammonia buffer is therefore the buffer for chronic respiratory acidosis. Sometimes this can be asked, what is the buffer for chronic respiratory acidosis? So ammonia is the buffer. Second point that we must understand is that the ammonia buffer, how does it work? It works by the mechanism called as non-ionic diffusion, also called as diffusion trapping. We did that in the first chapter in the general physio section. Remember that the H plus has to be eliminated into the urine. It's a chronic respiratory acidosis. Kidneys are going to cause the compensation. So H plus is to be eliminated into the urine. How does ammonia work? Ammonia, which is generated by the cell, now comes into the tubular fluid and it forms NH4 plus. You know, NH3 will take H plus to form NH4 plus. Now this is ionic form, and ionic form is less diffusible. Non-ionic forms are more diffusible, ionic forms are less diffusible. We saw that in the case of bicarbonate also, an ionic form, bicarbonate, less diffusible, less absorbable. Even here, it's the ionic form. So now NH4 plus cannot diffuse back into the cell. It's trapped in the lumen and it will be excreted into the urine. So ammonium will be excreted into the urine. That's how H plus was taken, trapped and eliminated into the urine. So this is how ammonia works. Now phosphates are also concentrated in the tubular fluids, 8 times more concentration as compared to plasma. We've seen that. I just want to add one more definition, and that is titratable acidity. What is titratable acidity or titratable acids? Those acids which are buffered by the phosphates in the kidney, the phosphate buffered acids which are eliminated into the urine, they are called as titratable acidity. Now why did this term came? Why did this term come? It's because we had to know how much acid has been eliminated into the urine and which are the buffers that did the function of buffering. What is done? Suppose, as we saw that there was a condition of respiratory acidosis and the acids are being eliminated into the urine. Naturally, the pH of the urine will be acidic. Let's say it has become 5 or maximally, as we saw, even 4.5. Now what we do is collect the urine sample after the urinary acidification has happened. Collect the urine sample and titrate it with NaOH, okay, the alkali, and bring its pH back to 7.4, which is the pH of the ECF, pH of the plasma. How much NaOH was required for this titration? We will see that, and from that we will get to know how much acid was buffered by the kidney and excreted into the urine, and therefore that is called as titratable acids which have been eliminated into the urine, right? So that's one definition that you should know. What is a titratable acid? The urine sample is actually titrated with against NaOH. Its pH is brought to 7.4, and from the quantity of NaOH that was required to cause this, we get to know how much acid was eliminated. But there is a slight hitch in this. We saw just now that there are 2 buffers in the kidney that are going to cause this buffering, the ammonia and the phosphate. So ammonia and phosphate both might have worked. Why did I say then that the titratable acid is the one which is buffered only by phosphate? There are two buffers in the kidney. Well, the reason is, look at the reaction. Urine pH 4.45. We have taken hypothetical figure, let's say 4.5 or 5 or whatever it is, and we take it to 7.4. You know what is the pKa for the ammonia buffer? Well, 9.0. Yes. So please remember one more thing, that the only buffer which has the pKa in the alkaline pH is the ammonia buffer. Please remember this. This is the only buffer that has a pKa in alkaline pH on the alkaline side. But then my point was that the reaction, this reaction, while we are measuring the titratable acid, it's going from 4.5 to 7.4. That means in this reaction, the acids buffered by the ammonia buffer cannot be included. The ammonia was not, could not have been active in this reaction, isn't it? Because its pKa is 9, whereas our urine sample, its pH is being taken from 4.5 to 7.4 or 5 to 7.4, whatever it is. So what do we get then? The acids buffered by phosphate. Phosphate pKa is 6.8. We know that, so it will come in that range. So just one more definition, titratable acids. We want to know how much buffer has been used and how much acid has been neutralized or buffered by that particular buffer. That was a little narrow, small concept about the buffers in the kidney. So this is the overall kidney function in the acid-base regulation. You know, respiratory acid-base disorders will be corrected by the kidneys in this manner. So that was, in a nutshell, physiology of the acid-base balance. I am deliberately restricting myself to this much part because I know, I mean, the Sigurd-Andersen normogram for that matter, or some biochemical reactions, they are taken in different subjects, and to avoid that overlap, I am simply taking that much part which is not covered in any other subject. So that's one. Finally, let me just add one more little concept related to this, and that is the anion gap concept. Well, I guess even this is taken in medicine, but however, I will just take the concept behind it. Well, we have a way of diagnosing metabolic acidosis. We want to diagnose the metabolic acidosis. In metabolic acidosis, what is going to happen? Acids have increased, so H plus have increased, and the alkali, that is bicarbonate, will decrease. That is what is the expected thing to happen. There is a way of finding out whether it is a metabolic acidosis or not, and what could be the possible acid and what could be the possible cause for that acidosis. And to find out this, we have this simple calculation called as anion gap. Now, what is it basically? Look, first of all, there is a law of electroneutrality. And this law says that the number of cations and anions should be equal on either side of the membrane or in a particular solution. That's a law of electroneutrality. So, even if we are talking about the serum or plasma or ECF, the number of cations and anions should be equal. Yes, it is equal. So, the equation should be something like this: sodium plus potassium. These are the routine cations that we measure. Apart from that, of course, the calcium and other cations. But some cations are complex to be measured. We don't measure them. So let's write it as unmeasured cations is equal to chloride. Now anions, chloride plus bicarbonate plus unmeasured anions, isn't it? Both sides should be equal. Law of electroneutrality. Now here what's happening is routinely all the cations get measured routinely in routine analysis, but all the anions do not get measured in a routine analysis. Some anions, they will stay unmeasured. And look, we are talking about bicarbonate as well. That is measured, fine. And bicarbonate is going to decrease because we are looking at a possible metabolic acidosis situation. So bicarbonate will be an important factor. It's going to decrease. But some unmeasured anions, some anions are not getting measured at all. And therefore, what will happen is a virtual gap will get created between the two sides of the equation. Actually, it should have been equal. Okay, so I'm saying it's a virtual gap, not the real one. In reality, these are equal, but the two sides are equal, cations and anions. So a virtual gap gets created and it is called as the anion gap. Okay, that is the concept of anion gap. A virtual gap that exists between the cations and anions. That's the anion gap. So how much is this anion gap? If I were to take this side on the other side of the equation, okay, this side cations, if I am taking it on the anions are being taken to that side of the cation, to the side of cation, then this minus this should have been 0, but that's not the case because, as I said, some anions remain unmeasured. So the thing is, what happens is sodium plus potassium minus bicarbonate plus chloride. So cations minus anions. Now interestingly, sodium is 141 milliequivalents per liter. Okay, let's not take potassium right now into the equation because potassium is not, we are talking about the serum or plasma, and major cation in the plasma is sodium. Potassium is very less in the plasma, 4 milliequivalents per liter, and that too is diffusing in or out of the cells very routinely, isn't it? Insulin is there, it will push the potassium into the cells. So potassium levels, which we take as 4 milliequivalents per liter, is changing constantly according to the situation. So we will not take potassium right now in the equation, and therefore actually we should write the equation as sodium minus bicarbonate plus chloride. Now sodium is 141 milliequivalents per liter, bicarbonate is how much? 24 milliequivalents per liter, we have done that already, and chloride 105 milliequivalents per liter. Yeah, so 105 plus 24, 129. 141 minus 129, right? Anions 129, and that means 141 minus 129 is 12 milliequivalents per liter. This is the normal anion gap. First of all, that's the normal anion gap. Clear about this? We have already said there should not be a gap actually, but this is a virtual gap first of all. Okay, since we have not taken potassium into the equation previously, just considering the potassium, it would be plus or minus 4. Potassium is 4 milliequivalents per liter. So if I take plus or minus 4 for potassium, and why did I say plus or minus? Because as I mentioned, that potassium, its level is very low and it's constantly diffusing between the extracellular compartment and intracellular compartment, and therefore plus or minus 4 considering on this 12, and that would be 8 to 16 milliequivalents per liter. That should be the range for the normal anion gap. 8 to 16 milliequivalents per liter is the normal anion gap, or if you take 12, that's also fine. Now coming to the diagnosis of acidosis, metabolic acidosis. You know, metabolic acidosis means the bicarbonate levels will go down, bicarbonate levels will decrease. Clearly, bicarbonate is an alkali. So if this decreases, that means the value of this bracket, anion bracket, will also become less than 129, clearly, and that means the gap between the cation and anion will widen. It will increase, the gap will increase. So increased anion gap, which can be seen just by measuring the sodium, chloride and bicarbonate in the plasma, we would know that it's a condition of metabolic acidosis. Okay, without measuring acids, actually we have understood that it's a metabolic acidosis by doing this calculation. So increased anion gap is a feature of metabolic acidosis. But then what's so big deal about this? Let me tell you what is the big deal. In many conditions of metabolic acid, look, metabolic acidosis can result from tens of conditions, you know, renal tubular acidosis, it could be related to the GI fluid loss, and lots of the ketoacidosis, so on and so forth. Now in some conditions there will be an increased anion gap because, as I said, simply the bicarbonate is decreasing. So this entire bracket, its value is becoming less. But in some conditions the anion gap will remain normal. In some conditions the anion gap will remain normal. You know why? There are certain acidosis conditions in which the anion of the acid is chloride. I repeat once again, we are looking at a possible metabolic acidosis situation. That's why we are doing all this calculation. And let's assume that in a certain metabolic acidosis condition, the anion of that acid is H plus, of course, anion of the acid is chloride. What will then happen? If the anion of the acid is chloride, then it's a metabolic acidosis condition. So bicarbonate is going to decrease, that is expected, but chloride will increase because metabolic acidosis. Acids have increased, and in a particular condition the anion of that acid is chloride. So if the acid increases, chloride will also increase. So see, bicarbonate decreases but chloride increases means what? The entire bracket will remain the same, normal, and that means anion gap will remain normal. So we get anion gap calculation for either first the diagnosing the metabolic acidosis, whether it's there or not. Second thing is, what is the reason? What type of metabolic acidosis is it? What is the anion for that acid? For example, in GI fluid loss, it's observed that when it results in acidosis, the anion gap remains normal. So, you know, we can get to know that, okay, anion gap is normal, means the chloride was the anion and therefore it was an acidosis, and yet it remained normal. Otherwise, metabolic acidosis, the anion gap is expected to increase. So that's about the concept of anion gap. I have just kept myself limited to the concept of the anion gap. Rest you will learn in the pharmac and medicine. What are those conditions in various renal tubular acidosis, like proximal or distal RTA, what things happen, you will learn that. But just remember, principally, if it's a normal anion gap metabolic acidosis, the reason is the anion of that acid is chloride. So this was the summary of the acid-base physiology. Disorders, of course, you will learn in the medicine. That would be appropriate thing to do, and therefore that's what it is. So we are done with this chapter of kidney and the acid-base balance.